They all have different minerals.
They all have,
They're not all the same minerals.
they're not exactly the same minerals? That's a similarity? What's a similarity?
This has a bunch of minerals. This has a bunch of minerals. This has a bunch of minerals.
Okay, they're all made of minerals.
That's how they're similar.
Okay, what else might be similar about them?
They're all granite.
They're all granite, okay.
They both have the pink.
They what?
They both have pink.
They, okay, well, there's 3 of them.
Oh, sorry. 2 of them.
Toby?
They all have black specks on
They
them.
all have black specks, okay. What's another similarity? There's one more that I want you to see. Tim?
We would say they're all rough.
You're all rough, okay. Elizabeth?
They're all igneous rocks.
They are all igneous rocks. Yes, Tanya?
They all have quartz.
They all have quartz, okay. What do you notice about their crystal sizes? Okay. They're pretty similar crystal sizes. You can identify the crystal sizes with your naked eye. So they're not so tiny that you need a hand lens to see
So
them.
they're uniform?
Are they uniform?
Uniform, they're all the same.
Okay, all right. So because you can see the crystals, because you can see the crystals in these samples, they're not enormous, but they're large enough that we can see them. This tells us that these crystals did not form on the surface of the earth. When lava flows, when magma comes to the surface and flows out on the surface, it cools very rapidly. And because it cools rapidly, there's not time for these larger crystals to form. So where do you think that these granite rocks were formed? Where were these granite rocks most likely formed? I'm not asking about like North Texas. Where from the middle of the earth to the surface of the earth, where these granite rocks formed?
The asthenosphere.
The asthenosphere, that's a great answer. The asthenosphere is the plastic part of the upper mantle. So that's where this stuff came from.
That's where it came from.
Yes, that's where the magma emerged from. But where did it go when it rose up? Where did it go to cool, to form this granite? Toby?
Formed underground, below the surface of the earth.
Below the surface of the earth, under the ground. And what might that intrusive rock, why did this granite need that condition to form?
It allowed it to be like an insulator, which caused it to form, crystallization could occur longer.
Longer, like longer crystals? What do you
It
mean?
could cool over a longer period of time for crystallization of larger crystals to occur.
Okay, so Toby's saying that because this magma cooled underground, that the earth protected or insulated that magma so the heat was released more slowly. And so the crystals had a longer time to grow. Did I summarize that correctly, Toby?
Yes.
Okay.
I think you did a great job.
Okay.
There's an example at Inks Lake where you can actually see where the magma was trying to push through at 3 different places, that you can see 3 different cuts of granite
Cool.
cutting through another layer of granite.
And we're actually going to see something like that next week. Yes, ma'am.
So, are we saying that these are the larger crystals?
Larger than what?
Small crystals that are fast cooling? I'm trying to just, with the discussion that we just had.
Okay.
Since they did not cool as fast,
The
meaning that they
larger
were on
the
the
crystal,
surface.
you can infer that the cooling time,
So this is an example of larger crystals?
yes,
Okay.
compared to your smaller crystals.
Compared to,
Now, if we compare that to our big room rock where we are crystals, those are tiny crystals compared to this big crystal. Right? So that, you, be careful about large and small because those are relative terms. Okay. Yes?
Can you give me a small crystal that I can use on a
Like-
reference? For reference, yes.
Well, look at your mineral samples.
Okay.
yeah, like if you're telling me it's relative, then how do I know that the sample is?
Dr. West?
I want to ask a question. Sometimes, would it help to take one of the scopes and put it on the screen to show the size crystals at this point? Or would you want to do that later?
I think we'll do that in a little bit. Yes.
So is there like a numerical chart that says if a crystal is between 1 millimeter and 2 millimeters, then it's pulled quickly and if it...
You know what, we are gonna actually investigate just that in a little bit. That is a great idea for us to have. So when you look at your rocks, did it look like some of the crystals, if you looked at your hand sample of granite, did you see crystals that looked like they were surrounded by other minerals? So what does that tell you about the order of formation of these minerals? Did they all form at exactly the same time? Does it seem like one formed first and then another one formed later? So maybe one formed at a higher temperature, and as it cooled, then that one stopped forming and another one formed around it? That's one way that these granite rocks end up looking like they do. So if you turn to the next page, this is a great geology tool called Bowen's Reaction Series. This tells you how rocks and minerals in rocks can form from higher temperature to the lower temperature. And it also relates it to the chemical composition of the magma as well. So you can see that the olivine, augite, hornblende, and mica form from one chemical composition, where the feldspars, the calcium-rich, forms at a higher temperature, whereas the sodium-rich feldspars can form at a lower temperature. And then the quartz, the muscovite mica, and potassium feldspar form at the lowest of temperatures. So just keep that in mind and think about this chart when you're looking at the minerals that are present in granite, because you see the composition from top to bottom. There's ultramafic, mafic, intermediate, and felsic. And granite is considered a felsic rock because it's got the feldspar and quartz mainly. And we're gonna talk more about that later. So just, this is a guideline about the cooling temperatures or the crystallization temperatures of different minerals. So if something cools, if crystals grow at a lower temperature, you know, it's not gonna be olivine, because olivines can form at very high temperatures before other minerals start to form. Okay? Yes, Craig?
In this chart, what would be the lava that's on the top? Like what temperature would that, or
Well, lava, when the magma comes out as liquid and it goes to the surface, it cools immediately.
so where is that on, which part was?
Lava will not have any crystals in it that you can identify.
So like the red lava rock, what is that made of? The one made of just everything, or is
All those pieces are it cooled so quickly that the minerals didn't have time to crystallize and form, so you can't even see any minerals in it. like obsidian is a mineral. It's volcanic glass. It cools very quickly. So no crystals were able to form. So we're gonna move on. Let's see if there's a question we're missing. So we see granite as the most common igneous rock because it is the most common igneous rock on the continents. It's a continental crust rock. It's what makes up the most of the continental crust. On the oceanic crust, you see a rock called basalt. That's the most common igneous rock on the oceanic crust, and it's more dense than granite. Granite is a very low density rock compared to the basalt. And we're going to look at those in a little bit too. Yes?
Is granite considered one of the bedrocks around here?
Yes. Igneous is, bedrock is like the bottom, right? So yeah, granite is, consider the granite on the bottom and then the sedimentary rocks fall on top of it.
That's not be a little off topic,
Yeah.
but since it's so common, why is it that granite is so valuable as far as utilizing in like home improvement stuff, like countertops, that particular area? What makes it so valuable?
Okay, if you want a countertop in your kitchen, would you choose granite or sandstone?
Granite, because
He probably wouldn't know.
So if you take a piece of sandstone, or let's say limestone,
Like it's smooth, like it feels better.
yeah? Well, you can polish any rock.
Say you're cutting a tomato, you wanna cut it on top of a sandstone, or you wanna cut it on top of a granite?
granite because it's less porous.
I don't know what
I
sense
took around the vine of sandstone.
Okay, so granite, look at the minerals in the granite and the hardness of the minerals in the granite. One, none of them reacted to acid. So if you spill vinegar or any kind of fruit juice, anything that has any kind of weak acid in it at all on your granite countertops, it's not going to dissolve, right? So there's step one, don't put marble in your kitchen. It's very pretty, but yes, it's very porous and it will absorb the colors. My sister keeps saying, because I spilled red wine on her marble countertop. Second,
They don't.
if you chose, the granite is made up of a lot of quartz, which is super hard and resistant. That's why people, when you see headstones in cemeteries, they used to be made out of whatever rocks were available, like limestone or marble or, sandstone even. And then over time, people have figured out that the elements, they weather, and so they wear down, and that's why people take rubbings of the gravestones to figure out who's there now, because it's weathered. Granite, on the other hand, is more resistant to weathering, and so they withstand the test of time. Yes?
I think his question was, why is it so expensive? Because it's labor intensive to get it out of the ground.
Yes, it's not just about the granite itself, it's about somebody had to go cut it, and cut it, and cut it, transport it, and then cut it, and polish it, and it is labor intensive. So if you want to go get some granite yourself, you could come up with a method to DIY. It's heavy because it's a rock, it's not the heaviest.
Isn't it heavier than your other rocks, or I don't know, is it?
It's not necessarily, depends on what it's composed of. Okay, guys, let's look at this. Okay, the silicates. This is the basic, just a little background on chemistry. We talked about the silicates being the most common group of minerals. Here's a silicon atom. It has a charge of +4. These oxygens come in, there's 4 of them that surround it to make a silicate tetrahedron. This is the building block. And we talked about diamonds versus graphite, and it's all about the arrangement of those atoms, right? So the arrangement of this silicate tetrahedron is what gives us the differences in all these minerals. So there's felsic silicates and there's mafic or mafic silicates. The felsic comes from feldspar. So the granite you have is considered felsic because there's a lot of feldspars in there. It's a silicate. It's less dense than mafic. It's lighter because there's less of those metals in there like iron and magnesium. And examples are mica, quartz, and potassium feldspars like you see in your granite. Mafic, on the other hand, has a lot, it's named because it contains magnesium. There's, the Fic is for ferric or from iron. When the tectonic plates move apart, the magma can come to the surface and cool, and that's where you're going to find more mafic rocks like basalt, which are composed of more mafic minerals like olivine and pyroxenes.
Where do they go to mine or find olivine?
You can find it in continental crust as well as it's not as prolific, yeah. Okay, so here are different structures. And we're not going to spend a whole lot of time on this. It's just kind of cool to see how these silicate tetrahedrons can come together to make different minerals. So when they're by themselves, they're not bonded to anything else. It's olivine. When they make a little hexagonal circle, they can string together like this, or these strings can come together, or then you can have a huge series. Mica, like muscovite, is a silicate sheet on top of another silicate sheet, on top of another, and weak bonds between the sheets is what keeps them together. They're very weak, which allows us to pull them apart. Now, on your table, quartz from yesterday, your mineral identification table that gave you the families, quartz was listed as an oxide because it is only silicon and oxygen. It is technically an oxide, but we consider it a silicate because it is made of silicon and oxygen. But all the other, they can have other things with them. So just be aware that this is kind of a moving line between the two. So here we are considering quartz because it has a silicate structure. We're considering it a silicate. Okay, we are going to do the coolest thing we're going to do all day. Are y'all ready? Okay. This is super dangerous. So everything needs to be cleared off. We're going to take a bathroom break while we get everything set up.
More than cleared off. So that means, as we said earlier, no big bags in the area, no purses or bags hanging on the back, because we've got to be walking through these aisles, so it's got to be as tight as it can be with hot single.
And there's some cleanup that we need to do. One, if you have your smart scopes available, this would be a great time to have them. You're going to need, if you have it and want to use it, great. You might want to have your phone for video. You will need, somebody will need some sort of timing device for time, a stopwatch. That's great. You do not need to have your hand samples. You can place those in the back. You will need to have, every person is going to have goggles on. So clean everything off that you can. Yes, put everything on your trays. Consolidate there. We have until 9:45 to start.